So in this video, we are going to see linear time-invariant systems. So representing a system. I know what is a system. I have some input sequence X and I pour it into my system. I have some input sequence Xn. Okay. So representing a system. What's a system? We all know we have an input sequence Xn, which I can pass to my system, let's say F or T. There's a slight change of notation here. Instead of F, I'm using T just to be consistent with the Oppenheim books notation. No other reason. And I get some output Yn. Now the system can be represented in this form by specifying T. So if I know T, given any input sequence Xn, I can compute my output sequence Yn by using this formula that this input sequence Xn, when operated upon by the transformation system T, then I get the output sequence Yn. In general, T can be of any complicated form and it can be very general. But for LTI systems, I can, which means linear time invariant systems, I can specify T in much simpler form. So I'll just be showing in the next slides how for an LTI system, T can be simplified so much that it is very convenient to mathematically manipulate it. Okay, so let's revise. What is an LTI system? So it's linear time invariant system. What is linearity? So let's say I have an input x1 n and I pass it through the system T and I get some output y1 of n. And similarly, if I have some input x2 of n, I pass it through T, the system T, and I get y2 of n. Now what will happen if I pass the input a times x1n plus a1 times x1n plus a2 x2n? So if I pass it through the system T, it could be some y3, but if it is a linear system, then it will be a1 times y1n plus a2 times y2n. This is the definition of linearity, and this is how you represent it. Another property now is time invariance. What is time invariance? If I have an input xn which I pass through my system T, I get some yn. And if I pass some input x dash n, which is basically x of n minus capital N, a delayed input. So my output should be also my y dash of n should be equal to y minus capital N. So this is what I represent it in this way. So this is my y, and this is my y dash. Y dash of n is equal to y of n minus capital N, right? So now, using these two properties, I can simplify T. Let's see how. So let us recall that we have got xn, and I can write xn. Basically, let us draw to be more clear. Xn can have some form. Let's say this is minus 1, 0, 1, 2, right? We have seen that we can represent xn with the help of single impulse input. This is 0, and it is 0 everywhere else. The unit impulse function delta of n. This is n here, right? This was my general xn. Now my delta n, I can represent x as in the form of summation of delta n's, the delayed version of the same and the scaled version, right? So basically I have to say this is x of k, which is just the scaling factor for delta n minus k, right? So I just and summed over all the k, basically minus infinity to plus infinity. So I take, so this basically I represent this in terms of individual impulses which are delayed in time, means that the timing information is preserved, and scaled in the amplitude. This is the scaling factor xk, right? Now let us put it in the form. Now in general, my yn sequence is equal to transformation of the sequence xn, right? Now I can substitute the value of xn from top, which becomes t of summation over k. K goes from minus infinity to plus infinity, so I just leave it as k here just for saving my time. Xk delta n minus k, right? But now I know that the system is linear. What is the meaning of linearity? It means this is my input delta function. This is just a coefficient, right? Dummy variable k. So I can, using the property of linearity, I can say this is equal to summation over k xk t of delta n minus k. This is because of linearity. Right? Now, what is delta n minus k? Now, let us see a single single output y of n. Now, my y of n will be equal to basically this whole thing and then followed by an n. So it will be t of the nth value in the sequence. So this is summation over k xk, which is the same thing, and t of delta n minus k. From this sequence I take the nth value, right? Now I know that I can write this in this form. Okay, this thing remains same, no problem. But this part can be written as t of delta n minus k, right? Which property is this? This is simply time invariance, right? You remember the definition of time invariance. Okay, so let's go to the next page. Now, this term, t of delta n, what is this? This is the response of the system to a unit impulse input, right? So let me call it as h of n. If I call it as h of n, this Okay, now what is this T of delta n? T of delta n is the response of the system to a unit impulse input. If my input is simply a unit impulse, I just pass a value of 1 at t equal to 0, n equal to 0, and everywhere else it is 0. What is the response of my system? I can call it as a sequence h, right? So what does it become? It becomes y of n is equal to summation over all k x of k h of n minus k. And okay, let me write the complete form, k from minus infinity to plus infinity. So this is an LTI system. So you can see that the LTI system can be represented just by specifying what is my h of n minus k. H of n minus k is simply the impulse response. So you can see here h of n k, basically h of n is simply transformation of delta n and the nth. So this is my h of n. This is called the impulse response, because this is the response of the system to a unit impulse input. That is, this is the y when your x of n is equal to simply a delta of n. This is what you pass to your system. The output will be y of n is equal to h of n. That is my. So in this way, I can specify an LTI system by just specify impulse response. And using this, you can construct output yn for any given input sequence xn. Okay, so in short, this is represented like this. So if I have an xn, I pass it through the system t, which the t can be now represented just by hn, and I can obtain my yn very conveniently using this formula. And this is the short form notation that xn convolved with hn. So this is called the convolution operation. Okay, I'll just specify one example here. For example, if you have a seed, so let us say this is my input at t equal to 0 or n equal to 0, I soak a seed in water, right? Let us say I soaked one seed in water. This is my x. So I soaked one seed, and what will be the output? After, let's say 10 hours, let me just use 10 here. 10 hours, I see the seed sprouts. I see one seed sprouts. Now, what will happen if I soak two seeds instead of one seed? Right? So if I were to soak two seeds, what will happen? The output will also be two seeds. Now if I seed another seed at t equal to 1, what will happen? At t equal to 11, I will get one more seed out, one more seed sprouting. Right? So this is like a linear time invariant system. Why is it linear? Because the more the number of seeds I soak, the more sprouts I will get. They are independent of each other. And why it is time invariant? Because it does not matter when I soak the seed. I may soak at t equal to 1 or 2 or 3, and correspondingly it will take only 10 hours to get the sprout. This is one example of a linear time invariant system, which will help you intuitively understanding what the concept is. Now let us see how do we compute convolutions. There is a very nice example in the book Oppenheim. So you have, this is my xn, this is my input sequence is given to me, and my system is hn, which is also given to me. So hn is basically if I give a unit impulse input, means I give 1 at t equal to 0, at n equal to 0, and subsequently at n equal to 1, at n equal to 2, I'll be getting these responses. The output will be this. Now the question is, if I have xn, what will be the output? You can imagine that I soaked one seed. Okay, this is like, if I soak one seed at t equal to 0, then this will be the kind of output I will get. Okay, so if I do it at t equal to minus 2, just at t equal to minus 2, what will the output? Same thing shifted to minus 2. Right? Now, so basically, mathematically I can say x of n, this component is basically x of minus 2 into delta n plus 2. Right? This is simply from the formula. This is n minus n. So here n is equal to minus 2 here. So this is what you get. Right? Now next is at x equal to 0. So see now at x equal to 0, this is my height. So okay, at x equal to 0, this is x0 times delta n, and the output will be x0 times h of n, basically this same thing, because this is anyways a delta function, just a scaled version of my impulse response. Now similarly for x equal to 3, I can write it like this, and my corresponding output is this. Now the principle of linearity says that you can just superimpose everything to get the final output. So when your input is a superposition, my output will also be a linear sum, a superposition of this whole thing. And this is what the final output becomes. Okay. Now let me show you another animation to help you understand. Let us say this is my input sequence, right? It's a periodic signal occurring at every after every 4 n instances. This is my n. So now, and this is my h of n. This is my impulse response, right? Now, what is the response of the system to this x of n? Okay, to compute it, we will do a procedure. We know the formula. Formula is y of n is equal to x of k h of n minus k summed over all k, right? K goes from minus infinity to plus infinity. Now, what is this h of n minus k? H of n minus k means you are, if I were to draw it with respect to k, you reverse it and shift it by n, right? Okay, let me show you. Okay, let us say in the first case here the n is equal to 0, which means you just flip it, and at n equal to 0, when n is equal to 0, okay, k, for k equal to 0, this is the value h0. For k equal to 1, this will be h of minus 1. So in this way, this is my h of minus n. Okay, now what will I do is, I have fixed my n, so n is equal to 0. Now I sum over all these things, and if I multiply xn with hn, that means basically x of k and h of 0 minus k, then the product, only this term will appear and sum will be just this term, right? Now next, let's go to n equal to 1. Now for n equal to 1, this is my x of k, this is my x of k, and this is my h of n minus k. So here n is 1, so it is h of 1 minus k. So this is how the plot will look like. Now if I multiply these two, element wise multiplication, and then summed over the thing, then only this term will appear, right? And this term is here. Then I go to the next step, which is at n equal to 2. At n equal to 2, h of 2 minus k will look something like this, and then I will get, if I multiply element wise, I get only this value which appears here, and that's how I construct the entire output sequence. This is the convolution operation. Okay, so with this we understood what is an LTI system, how do we represent it in terms of an impulse response, and how we compute the outputs given any input if I know the impulse response of an LTI system. There is a question for you. Now if xn has a length nx, which means number of consecutive non-zero entries, so if this is my n, this is my x of n, so consecutive minus 1, this is non-zero, everything else is 0, this is non-zero, this is okay. I think it could be said maximum range of non-zero entries. So all these entries, let's say, are 0. Okay, then if xn has a length of nx and hn has a length nh, what will be the length of the convolution, basically the output? So this is a simple question. I hope you can solve it very easily. Thank you very much. So these are the references. You can look at Oppenheim chapter 2 section 3. Thank you very much.